Okay, so today's the fourth lecture, maybe the last one, maybe we'll have an extra one. It's not clear we'll be able to cover everything, so it's up to you whether you want me to do maybe an extra hour next week or so. Up to you, if you're interested in the contents. And so thanks of course to Ricardo for organizing, and so today it's a bit ambitious. I should have covered states last time, but I didn't finish, so I'm going to cover states today. And then hopefully I'll talk about some applications. So the references for states, I mean, it's a very rich subject, but I would say this is an extremely precise account of everything that has to do with states in algebraic quantum field theory. This is an excellent introduction. It also provides some intuition for a modern perspective on the Hadamard condition that we will not cover based on something called microlocal analysis. But it's explained here from a very intuitive point of view. And classics, maybe for a little bit more applied stuff and for green functions, very advisable is Birrell and Davis, and Fulling is also excellent for everything that has to do with green functions and how they relate to states in quantum field theory. And for black hole radiation, there's a little paper from 2014 upon which I will base some of the discussion by Jorma Loco and myself. And there's also a very nice discussion in Birrell and Davis, this classic monograph from the 80s. Very, very accessible. And for QFT and ADS, I think there's two papers that really do it in a very rigorous way. One of them is more mathematical than the other, so I suggest reading the non-mathematical one by Da Piaggi and Ferreira. So Ferreira was visiting us. It's Hugo, if you remember. He visited us last year. And there's another classical field theory paper by Da Piaggi, Ferreira, and myself, which will, if you're interested in that and want to keep an eye on the archive, will eventually go to quantisation as well, but for now it's all classical. Okay, so it's not clear that we will get to here. I'll try to cover F and G, and maybe we can talk about the last subject some other time, maybe next week if you want. Okay, so in any case, I would be very schematic on this last point. Okay, so states. Before that, let me perhaps recall what the GNS construction is. So GNS is some construction which you can think of as a machine in which you start with an algebra of observables and states going from the algebra to complex numbers, which are linear and positive functionals, as we've seen. And this is an algebra generated by the Klein-Gordon fields smeared against test functions which are smooth and of compact support. Okay? And the point of the GNS construction is so this is the input, and the output is something, it's a triple, right? So it's a dense subspace of a Hilbert space, a representation that takes algebra elements and maps them to densely defined Hilbert space operators and a vacuum state. And this is the standard quantum field theory Hilbert space-based approach, right? There was one point I realized when looking at my notes that there was the very last point when I talked about how to represent operators in terms of these one particle Hilbert spaces and so on, that was actually wrong, because I said that, well, I'll tell you what I said that was wrong, but let's take one of these, let me call it phi hat, just to make the, make the eye think that this is a concrete operator in a Hilbert space in the usual way that we write them, okay? And I can write it as IA KE F minus I A star KEF. And then I said something wrong. I talked about this one particle structure, which is this K map going to a one particle Hilbert space. And so actually, I was misled by notations. Okay, it's a map which goes from solutions to, indeed, a one particle Hilbert space. But the one particle Hilbert space is not this one. This one is the whole Fock space. So let me call the one particle Hilbert space H like that. So this is a one particle Hilbert space now. And H is the Fock space. And the thing that you get by acting with the operators is the dense subset, which is indeed equal to taking every element of the algebra, representing it as an operator on the Hilbert space, and acting on the vacuum. So that's the precise statement of the last, maybe.
What was the definition of dense in this context?
Yeah, dense means that every vector in the Hilbert space is either in D or is a limit point coming from a sequence in D. Yeah. And it just comes from the fact that we just complete D to obtain the Fock space H, right? Because we take D and we realize that there are some Cauchy sequence that have limit points outside of D. We simply add them, and this gives us the completion, which is so by construction this is dense, right? The only points that are not in D will be limits of Cauchy sequences. Okay. So that's this bit was explained wrong in the last bit of last lecture, and this is the correct way of thinking about that. And let me just emphasize that this is a one particle Hilbert space. Okay. So now let's go to states. So states. So from this point of view, we said states as a maps from the algebra to complex numbers. And in particular, we mentioned that we were interested in states that are quasi-free or Gaussian, namely that are determined only by the two-point function. Okay, so if I tell you what this is, I can tell you any endpoint function of the state, and I know everything about it. In particular, vacuum states are quasi-free, okay? And with the GNS construction, we like to think that the state, the vector omega with respect to the algebraic state little omega is simply the following. Okay, so it's just the standard two-point function that we know from textbook quantum field theory. And okay, so now I want to be a little bit more concrete and really go on to analyze some of the properties of states. And I think the best way to do this is, so of course this is complex number. And it's a complex number, you'll see why. For those of you who are not familiar with this. And I think the best way to do this is to think of the Minkowski vacuum first and foremost, right? So let me start by thinking of the Minkowski vacuum here, right? So one particular way to think about states is to think of them as bidistributions. So I just act with these fields in terms of the mode expressions in the vacuum, and I get an expression that I can handle very explicitly. Right? So I want to think of the Minkowski vacuum, 2-point function, as an integral kernel. So in this form. What does it mean? Well, it means that so when I view this as an integral kernel in this form with 2 points, 2 spacetime points, it means that I can take two functions f and g and map them to a complex number. In which way? Well, let me think of, as usual, smooth of compact support. In which way? Well, I call this the integral d for x, d for x prime, f of x, g of x prime, w x prime. Okay, I want to think of it this way, and this guy, when I look at it as the sum over modes, has the following form. And maybe you'll be familiar with this expression. K e to the minus I k naught t minus prime plus I k. Okay, so this is a standard expression for the Minkowski 2-point. In a sense, what I've written here is more general than the 2-point function, because I need to do a complex integral in k naught to see what I obtain as a 2-point function. So depending on how I contour in the k naught integral, so you can see. This k naught is really off shell. It's not in any sense square root of k squared, blah, blah, blah. Okay? So, but you can see that there are some poles there. So I can perform this integral as a contour integral, and I can obtain the 2-point function if I perform the contour integral in a particular way. But I can also obtain the Feynman propagator, the fundamental solutions, and so on. So this is giving me a lot of green functions, and it will depend how I perform the contour, what type of 2-point function I get. Right? Okay. This one in particular is the Weidmann function, right? Because it's that's the form of a Weidmann function. If you would put a t here, that would make it the Feynman propagator, and so on. Okay. So I thought I wouldn't right away tell you how to do all those contours. But I thought I would tell you that what's important is to think of it as a to think of it distributionally, and in the sense the way in which I perform the contour is given an I epsilon prescription and doing that integral with that I epsilon prescription, right? So in particular, for example, if I write that if I take my t minus t prime and send it to t minus t prime minus, is it minus I epsilon? Yes, if I take my t minus t prime and send it to some t minus t prime minus I epsilon, then I shift the pole, and I can integrate on the complex plane, and indeed this is the prescription for obtaining the Weidmann two-point function, which is this one. Okay, so upon doing that and performing the integral, you can view this so this is still the Minkowski-Weidmann function. So this is exactly this expression here. So let me call it the Weidmann function. So this is once I have prescribed how to do that contour integral. Okay. So this is exactly this guy here. Okay. And of course, this is a modified Bessel function like the ones that we found when we did the Fulling-Rindler quantization, except back then we had a different index down here. Now this is just a 1. Back then it was an ij, if you remember, where j was the spectral parameter that we were using. But this is the sort of the space-time version of the two-point function in Minkowski. So this is equal to what? So this is equal to the Minkowski vacuum, and the field x prime, Minkowski vacuum. Okay. So this is what this is. Okay. You can see I can get this expression integrated against test functions and get a complex number, right? In the sense that I have written it here. Okay. Is everyone more or less following the discussion? Okay. Now, for the purposes of curved space-time quantum field theory, the Minkowski vacuum is really a very good reference, because we will need to renormalize to obtain expressions that we would like to get that are not linear in the field. So for example, if I wanted to obtain the vacuum polarization, right? The vacuum polarization, which is this. So you can see naively what I would like to do is to take x prime to the point x, and that would make it a phi squared. So the problem is, of course, that this guy is a distribution, right? So what it does is it maps some test functions to a number. It's a bidistribution. It's a distribution with two entries, right? And typically with distributions, you cannot do that, right? So imagine, for example, if I had a delta function, right? Delta x. Delta x is a distribution, which in particular takes the function f. Let me call it delta sub x. It takes the function f, and it takes it to f of x, which is, say, a real number if this is real valued function. Okay. So what does it mean? It means it takes f and it maps it to integral dx f. Maps it to integral dy dx y f y equals f of x, right? So the delta function is a distribution. So what happens if I want to multiply two delta functions? I get something that is too singular, right? So if I have dx prime, dx prime is nice. I can integrate against the delta function in x and a delta function centered in x prime. But if I wanted to multiply delta x at the same point, if I wanted to bring the 2 points together, this integral would diverge and it would stop making sense. So this is the problem that we have when we want to obtain these kind of observables like vacuum polarization, or more importantly, the stress energy tensor. So, and this is what's behind renormalization, is the fact that these quantum fields, which we are very used to writing like phi of x, are really distributional. They're in this form, when I represent them as operators on a Hilbert space, they're operator-valued distributions. And the story of renormalization is really a story that tells me how to prescribe taking the limit from x prime to prime and being able to cook up stuff like phi squared. Right? That's what renormalization is about. It's about handling distributional singularities. Okay? And so to handle distributional singularities, of course, we have to know the singular behavior of this distribution. That's the whole, that's the whole game in some sense. So, let us do that. So I want to imagine bringing x and x prime close to each other. Let me go to here. I want to imagine bringing x and x prime close to each other for that expression. Okay. And I want to say that this is the Minkowski one. Okay. Because that's what it is. So I want to imagine, right, bringing x close to x prime to analyze the distributional behavior of this object. So what do we get if we try to do that? And I'm in 3+1 dimensions now. And from now on, I'll be in 3+1 dimensions, and I'll tell you how to go to something that is not 3+1. And typically, the distribution, the singularity behavior depends on the dimension. And the higher you go in dimensions, the more severe the distributional singularity is. Maybe I'll make a comment about that in a minute. But first, let's concentrate in 4 dimensions and try to take those points close to each other. And I'll tell you what this symbol sigma epsilon is, okay, in a minute. Sigma x. prime times log. What do I want to call this? And this is smooth. This is smooth. Right. So let me tell you what this is. This is called the squared geodesic distance. So what it means is I take the point x and x prime, and I take a geodesic that connects them, and I square that, essentially. And it's also known by the name of Sinch's world function. So in Minkowski space, I'll tell you what the epsilon stands for. In Minkowski space, so this is what? Okay, that's square geodesic distance between a point x and a point x prime. Okay, and what I mean by sigma epsilon is simply that distributional prescription that I've done here. So namely t minus t prime minus I epsilon squared plus. And we call that a regularized square geodesic distance. Okay. Now you can see that when we try to analyze the behavior when x goes to x primed, if I naively remove the I epsilon prescription, this becomes singular when x goes to x prime, so namely when t goes to t prime, and when x goes to x prime. This goes like 1 over divergence squared, yes? And then there's another piece, which is a logarithmic divergence. This is a Bessel, by the way. Did I say that? This is a Bessel function. I1 is a Bessel function, okay? So this comes from looking at the short distance behavior of that modified Bessel. And this smooth is just it's a piece that remains smooth when x goes to x primed, okay? Right, so the distributional behavior of the singularity is 1 over singularity to the power 2 plus a logarithmic singularity. That's how it looks when x goes to x primed. And in a sense, what we want to do is we want to subtract that singular behavior whenever we take points x goes to x primed, and that's what we mean by renormalization in a covariant way. Okay? Is everyone following this idea now? Yeah? Yes? Cristobal? Yeah. Pedro? Yes. Kind of. Okay, good. So again, I emphasize knowing the distributional singularity behavior is important to being able to renormalize and obtain complicated observables like phi squared or eventually the stress energy tensor. And I want to also emphasize that if we were to define any state, say through the GNS construction or by any other way that we can imagine, if we wanted to define any state, it could or could not have this distributional behavior. Namely, it could have this distributional behavior that goes like 1 over things squared plus log, or it could have some other complicated distributional behavior. It could go like 1 over divergence cubed or something like that, okay? Now, what is important for us and what is important for physical states is, in a sense, that they have the distributional singularity behavior defined by Minkowski. So namely, that if I write a state in Schwarzschild spacetime, right, and I want to take the singularity structure of the two-point function in that state, it's important that the limiting behavior of x goes to x prime or x prime goes to x has exactly this form. If it doesn't have this form, then it's not a good state for doing renormalization, and we call it an unphysical state. If it has this form with, written in a more careful way that we will in a moment, it's called a Hadamard state. So a Hadamard state is a state whose two-point function has a distributional behavior that matches that of Minkowski. It can globally look very differently, but when you take 2 points together, the leading singularities are of this form. That's called a Hadamard state, and it's what we use as physical states in curved spacetime. And all the relevant, states, if you've heard about the Unruh vacuum or the Hartle-Hawking-Israel vacuum in Schwarzschild space, they all have this distributional behavior in the limit x goes to x primed, okay? And they are called Hadamard states, okay?
Benito, perhaps it's important to stress that you're doing renormalization even for free fields. I don't know if you mentioned that.
Yeah, well,
because in some
sure.
field theory we're used to renormalization only when we have interactions.
Yeah, this is renormalization. Yes, indeed. I mean, we're in a free Klein-Gordon theory. It's a linear theory, but there are observables like the stress energy tensor that, as you know, are not linear in the field, are quadratic, and so this requires renormalization. They're not linear observables. To define them entails imagining being able to take point x prime goes to x in this kind of expressions or more complicated expressions, but of this sort. And as I said, these are operator value distributions. We cannot in general put distributions at the same point and hope to multiply them like standard smooth functions say. And we need to indeed subtract some of these divergent behaviors to be able to do it properly. So for the stress energy, so even in a linear free Klein-Gordon theory, if you want to look at their stress energy tensor, you will need to renormalize. Okay, that's the idea. Yeah. So we are definitely not looking at interaction theory. That's even more complicated, and we will not do it in this.
You have to renormalize because of composite operators,
Yeah.
and also because of
Yes, absolutely. Yeah. But the advantage of this Hadamard prescription is that you can renormalize composite operators and potentials like phi cubed or phi to the fourth or so on in the same, in the same framework, right? But yes, of course, you could, if you want to get the stress energy tensor of phi to the fourth theory, then there's two things that you have to renormalize, right? Okay. So, so let me go to maybe before I get to renormalization, I would like to say a few more things about these two-point functions and how this I epsilon prescription is important to know what two-point function you have. So before we go there. So remember last time when we were looking at classical field theory, we already found, in a sense, two-point functions that, even I would say 3 of them, that were quite relevant. We found this E plus, we found E minus, E minus minus E plus. And we could have built E minus plus E plus if we wanted to, where this is the retarded fundamental green operator, this is the advanced green operator, this is the advanced minus retarded, and this would be an advanced plus retarded. And remember that one of the conditions when we wrote the algebra, so namely the commutation relations, remember that this was minus I E F G identity. If you remember, this was one of the axioms defining the Klein-Gordon field algebra. So this is, of course, an identity, and when I run through the GNS construction, I know that the identity gets represented as the Hilbert space identity. Okay? This is just one of the virtues of the GNS construction. So in particular, I know that if I represent this in a Hilbert space, this relation, I can simply put hats here and an H down here. And this is the way it becomes represented on a Hilbert space. And now that I have this is concrete operators on a Hilbert space, this is a concrete operator on a Hilbert space, and I can, of course, take its expectation value. And of course, oh, I forgot something here. And of course, the expectation value of the identity operator is unit, right? So this is just that, right? So in a sense, here we have a 2-point function, which is the expectation value of phi of f, phi of g. And here we have another 2-point function, which is the expectation value of phi of f, phi of g minus phi of g, phi of x. And it gives me, as a result, this. This is called the anticommutator function in a quantum setting. It is, of course, coming entirely from the classical theory, right? There is nothing quantum in order to define this advanced minus retarded, but it turns out that it's also the antisymmetric 2-point function, right? And people call it the commutator function. Okay, so that's just one of the 2-point functions that you can get in quantum theory. Of course, there are these advanced minus retarded that you could relate them to other 2-point functions in quantum theory, but they will, in general, also, well, they're of course entirely classical. So you would have to make a combination of 2-point functions that get rid of all the state dependence to get them out of some expectation value like that.
And in that construction that you have done, can you make sure that that commutator, for example, for a space like distance is going to be 0, like in usual Q of t? Because yeah, because this is causal. That's where you're going, right? It's by construction causal.
It is by construction causal. Okay. So of course, this is also this completely respects the causality of this friend of ours. Okay. Yeah, I mean, of course, this is a sort of smeared version, but you could write it as a kernel, right? And with x and x prime spacetime points. Yeah, of course, you are correct. So anyway, using these I epsilon prescriptions that I have now erased, but let me go to let me go to Minkowski space again. Right to the end. So writing this two-point function in this form, I can choose to take different contours in the k0 integral and get different two-point functions like this one, or like the Weidmann function that I just mentioned, or I could get the Feynman propagator as well, and so on. Okay, so let me tell you what those prescriptions are. It all amounts to taking contour integrals. So it turns out that this is a green function for the Klein-Gordon equation. And so namely, if I apply the Klein-Gordon operator like this, I should be able to get f or maybe 0 or, but you know, it helps me get solutions. F or maybe 0 if it's the anti-commutator, something. The point is, it's a green function, and it can help me get this advanced, this retarded, this advanced minus retarded. It can help me get the Weidmann two-point function, the anti-commutator function. It can help me get the symmetric Weidmann two-point function, which is also called, I think, the Schwinger function, and so on. And it depends how I perform the contour integrals, and it also gives me relations between the different two-point functions. Okay? So for example, if I wanted to get the retarded one, then I would perform a contour integral in this sense. Hold on a minute. Yes, this is wrong, of course. This is k0 squared minus k m squared. That's right.
K squared.
So here I have the real part of k0. Here I have the imaginary part of k0. And here I have the poles, which are a plus, that's right, a plus or minus square root of that. Right? Because if I take the square root of that and I square it, I get this expression with a positive sign. And these are the poles. And I can choose to take the contour like this when I integrate. And this gives me the retarded fundamental green function. I could also choose to do it the other way around, and I would get the advanced. Okay? I would get the advanced. So these are these poles, right, guys? These are the poles of this integrand, so that the zeros of the denominator, right? So there's two of them. You can see if I take the square root of that expression, I can square it and get two poles, one on each side along the real axis. And I could get the Feynman propagator in the following way. I could get the fundamental advanced minus retarded if I integrate in the following way. and so on. And if you want to, let me just say that the Weidmann two-point function is the following. And if you want to play with this expression, putting I epsilons in the right places to get these contours, you'll get the distributional representations of the different Minkowski two-point functions. And now let me just stress that, you know, in this way you also get some nice relations. So for example, you can relate the you can obtain relations like this one, right? Sorry. Weidmann plus Weidmann. What do I want to call this? Bar. So this just means switch x prime and x. Okay. Is equal to minus 2i the cream function minus e minus e plus. You can get relations of this kind, for example, between the Weidmann function and the Feynman propagator and the fundamental advanced and retarded solutions. And you can get many relations by just looking at these contours in Minkowski space and so on, right? The point is to know where the quantum stuff is. So as we have seen in the previous lecture, these guys, the E's that I have written here, all of these guys can be constructed out of classical field equations. They are simply a property of the partial differential equation that defines the Klein-Gordon field in the classical way. Also, the quantum Klein-Gordon field satisfies the Klein-Gordon equation, but already it's a classical thing where the state really becomes important, namely where you cannot get from the classical equations are when you try to get something like the two-point function, the Weidmann two-point function. So the Weidmann two-point function is a two-point function that knows quantum stuff. And in particular, its symmetric part has all the information of the quantum state of the Minkowski vacuum, right? So as you can see, for example, the antisymmetric part of the Weidmann two-point function, if I write it like, let me do that. This means symmetrize plus 1/2 the antisymmetrized part. But the antisymmetrized part is this. So let me just right away write that this way. So you can write the Weidmann two-point function as a sum of its symmetric and its antisymmetric part. The antisymmetric part is completely determined by classical field theory. It's coming from the PDE properties. But this part you cannot get from the classical problem. This contains all the quantum information of the state. And you can see, for example, if you want to get to the Feynman propagator, you can also do it. You can only do it if you know the quantum stuff. So because it's related to the Weidmann function in this way, right? So it'll have of course some piece that is classical. If I just solve for this equation and write the Feynman propagator is equal to what would it be? I half times this sum plus the advanced plus the retarded, then you will see that it has it has a contribution that comes from classical stuff, but it also has a contribution that is quantum. So in other words, things like the Weidmann two-point function, the symmetrized two-point function, the Feynman propagator know quantum stuff about the state and in fact define the state completely, whereas things like the advanced, retarded, and advanced minus retarded, and so on, are classical objects that can be determined even without knowing anything about quantum field theory, even before doing quantization, right? So I just wanted to point that out. This is very, very, very well explained in Fulling's book, which is one of the references that I wrote at the start. And if you want to really look at that in detail, I suggest you to go there and have a look. So let's take a 5-minute break now. Okay? Okay, so we're back. And so now I thought, so I've erased everything from the board except for this, which has the singularity structure of the Minkowski Weidmann two-point function. And what I want to do now is to take this singularity structure and generalize it to curved spacetimes. And this is going to be what we call the Hadamard property for a state. Okay? So I'm going to write a definition. Maybe I'll do it up here. Okay? So I'm going to write a definition. And it's not going to be completely... I'm not going to give a super precise definition, blah, 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 with all the detail. This is not a mathematical definition, this is a physicist's definition, right? Because otherwise it gets more technical. It doesn't get very technical, but we might have to spend another 10 minutes or so talking about it. So I'm concerned with globally hyperbolic spacetimes, okay? And I'm concerned with a Klein-Gordon algebra defined on that space-time. I think we were using this notation before. We were using this notation. I'm in 4 dimensions, but it doesn't mean that you cannot go to higher dimensions to define an analogous statement. And I'm defining, and I'm taking a state, right? I'm taking a state which goes from the Klein-Gordon algebra to some complex number. Right? And I'm going to try to understand this state in the distributional sense in which I have explained before here and on what I wrote on this side. Okay? So I'm going to view the state as a distributional kernel that takes smooth functions and gives you a number out of it, a complex number. Okay? Takes 2 smooth functions and it gives you a complex number. And I can view it as a distributional kernel. Okay, so it's a bidistribution with an I epsilon prescription. And I'm going to think of the Weidmann two-point function. Okay. So a state omega is called Hadamard if for x and y in, and I'll tell you what n here is. So n is a subset of M, which is causal normal neighborhood. Okay, so there's a technical definition for this causal normal neighborhood. What it means is that the 2 points are in a sufficiently close neighborhood that you have geodesics that connect them, and the geodesics are unique. Okay?
And contained in the set.
And they are contained in the set. They're contained in a set. They're contained in N. Okay? So you can view. So for example, you can view X, Y. This has a past cone like this. This has a future cone like that. There's a diamond here. N is here, and there's a geodesic there that connects them, and it's completely contained in N, and this is M. Okay, so it's just it's a technical definition, but the intuition is that you have unique geodesic connecting them, fully containing the set N, where the points are. Okay. Right. Then the Weidmann 2-point function satisfies omega, no, w xy minus h xy is equal to some xy with w. Okay, so this is a little w, this is a big w, this is a Weidmann function. Okay, so you can, for example, if you want to keep track, you can call this w epsilon to make reference to that I epsilon prescription, and so I want to call this 0 plus, meaning epsilon is evaluated at 0. Okay, so this is now an arbitrary globally hyperbolic spacetime, a Klein-Gordon algebra defined on this spacetime, and a state going from the algebra to complex numbers. It has a 2-point function that I have prescribed in some algebraic way. And the Weidmann function minus some quantity, some bidistribution that I'm going to define now, has to give me some smooth bifunction little w, okay? And what is this bidistribution here? Well, that's called the Hadamard parametrics. So it has a contribution that has a singularity that goes to 1 over singularity squared, much like our friend here. Maybe I'm missing something there, actually. So it has that 1 over singularity squared plus a function vxy log of sigma xy divided by lambda squared. Okay, and now let me tell you what these guys are. So this capital delta is called the Van Vleck Moret determinant. It's smooth. It's a smooth bifunction, and it has a value on the diagonal equal to 1. So if I evaluate x equals to y, it goes to 1. So this is a standard object which is defined by some, it's defined recursively with some series. By a set of differential equations perturbatively, and it defines this object. It's a standard object. Okay. Now this L is a length scale. So it's a real number. Okay. Nothing more than that. Arbitrary. Now this is the regularized square geodesic distance. Of course, it takes this form in Minkowski space, but in general, it will take a different form in spacetimes that contain curvature, right? So it's just the geodesic distance between the points x and y, and with an epsilon prescription, which I will write now. Okay, so the I epsilon prescription is I take a time function, okay? So I take a global time function, so I'm assuming that this space-time is time orientable as well. Let me say that it has a time orientation. I take a global time function, it doesn't matter which one I take, as long as it's a global time function. And by the regularized square geodesic distance, I mean take the square geodesic distance and add this 2I epsilon with the difference of the time functions at point x and y, and add also a epsilon squared. Right. What else do we have? We have these guys, we have the L, we have that. We need to tell you now what V is. So Vxy is obtained as a sum from n equals 0 to infinity with some coefficients that are smooth by functions and with powers of this square geodesic distance times a smooth functions which takes as its argument some number Cn times the square geodesic distance, and I'll tell you what the smooth function does. This is where it gets a bit technical, but let me try to do my best to tell you. So x is going from R to the interval 0, 1. It's smooth. Yes. Is equal to 0 for R greater than 1. P of R is equal to 1 for R greater than 1/2. And in between, it interpolates between 0 and 1. Okay? So it's a switching function, right? So it switches on when 2 points are sufficiently close, and it switches off when they are far apart. That's the idea, okay? Switches on when the points are close, switches off when they're far apart, okay? And the Cn are strictly positive. Strictly positive, increasing, strictly increasing, I think, even. Increasing sequence of real numbers. Okay? It's just a bunch of numbers that are positive and increase. Okay? And what are these? What are these Vn? Okay, what the Vn are, let me write it on this side. So the Vn are smooth, and they're called smooth Hadamard coefficients. Hadamard coefficients. That guarantee that H naught n, I'll tell you what that is, xy with h epsilon n equals 2 pi squared sigma epsilon plus. Okay, that guarantee that this, which is essentially, is morally speaking the same as that, but up to power n, right? And instead of taking this complicated form for v in terms of these vn's and that switching function, you forget the switching function and you just keep the vn coefficients up to power n, okay? Is a local y parametrized. That means that for each y, it is a local solution up to order n, to order capital N, to the Klein-Gordon equation for positive epsilon. In other words, the Vn's you obtain as a recursion relation out of the Klein-Gordon equation in such a way that for each value of n, this is a solution for each fixed y of the Klein-Gordon equation up to order n, okay? And keeping the epsilon positive, okay? It's a complicated definition, but that's what it is. Okay, so these Vn's guarantee in particular that for each y, this expression will also be a solution to the Klein-Gordon equation up to smooth terms, okay? So I need to continue, but I don't want to erase, so I'll do a little box here. So let me write a remark. Changes in chi or the Cn contribute smoothly to the definition. Therefore, the definition is independent of these changes because these changes contribute smoothly and they can be absorbed in W, in little w. So W just needs to exist, as you see. Then, okay. Then definition is independent of them. So, the definition is independent of them in which sense? In the sense that I only need any chi that satisfies these properties, any sequence Cn that satisfies these properties, and any smooth by function W such that this holds for the state to be Hadamard. It doesn't mean that I need a particular switching function and some particular coefficients and a particular smooth by function. I can choose just any combination of them such that this is true, and that makes the state Hadamard. Okay? And the next point is that the definition is also independent of t, the time function that we choose. So we can choose whatever time function we have in our globally hyperbolic time-orientable spacetime. And again, changes in this definition will not affect the structure of the definition of the Hadamard state. Okay?
the idea behind this is that your H function here will, yeah, so it will cancel the divergent part when
Exactly.
X and Y become the
Go
same
to a
point.
yeah. That is exactly the idea, and it is exactly this structure that you see here, the structure that we have
Yeah.
in the case of the Minkowski state, except this is completely tied to one particular state, and this is just telling me, give me one state in some curved space-time and be it such that this holds and it's a Hadamard state. So in particular, of course, this one is a Hadamard state. Yeah, and I'll give you now the trivialist possible example of a Hadamard state, which is even more trivial than that. So massless Klein-Gordon in Minkowski has the following two-point function. Okay, and so it has this singular behavior, and all the Vn and this V in particular is 0, and it's just that. That's the massless Klein-Gordon Weidmann function. Okay. Another comment that is maybe worth mentioning now is that this I epsilon prescription tells me that this is the Weidmann function, but I could give a different I epsilon prescription. So for example, I could define things in terms of a tilde regularized square geodesic distance, for example, in this way. And perhaps some of the coefficients would change in the front or something like that. I'm not entirely sure. It's not important. You would just fix these coefficients in some way. But you could, maybe by a factor of 2, you know, or something like that. But you could define the Hadamard two-point function in terms of some regularized square geodesic distance of this form. And this would, for example, be the Feynman propagator. So it's just a different I epsilon prescription, and this is the Weidmann, this is a Feynman propagator. I could define it in terms of the symmetrized two-point function as well. The point is I have to use one of these quantum two-point functions, the Feynman, the Weidmann function, or the symmetrized, because these are the ones that know stuff about the state. I could never define the Hadamard condition in terms of, say, the advanced Green operator or something like that, because that just doesn't know anything about the state. Okay. Okay, so this is just the definition of the Hadamard condition. Is a bit convoluted, but the intuition is indeed what Cristobal just said. It's just take the singularity structure of Minkowski and extrapolate it to curved spacetimes. So now I want to tell you what you can do with this. Let me just, before anything, go to a final remark. Maybe you can write it together with this list. So remark. The singularity structure depends on the dimension. Dimension dependent. Definition. In particular, the singularity structure will become more and more singular as you go to higher and higher dimensions. So the singularity structure in 4 dimensions is 1 over sigma. The singularity structure in 5 dimensions is still 1 over sigma. But when you go to 6 dimensions, it increases. I think it's 1 over sigma to the 3/2 or something like that. I don't remember. And if you keep going up, then the singularity structure will keep, the leading term will be becoming more and more singular. And a curious one is in 2 dimensions. In 2 dimensions is logarithmic. So this is the leading singularity in 2 dimensions. Okay. So remark, there's a dimensional dependent definition of Hadamard. And I give you a reference now. C. De Canini and Folacci, 2006. Okay, this paper has the Hadamard, the expression for the Hadamard parametrics in terms of the Feynman propagator in all dimensions greater or equal to 2. Okay. So let me get to the stress energy tensor renormalization, which is, of course, something that we would like to see in curved spacetime. Stress energy renormalization. So the prescription that I will give you is covariant, meaning it doesn't depend on some splitting in 3 surfaces or anything like that. It's a covariant expression. And it's a prescription that was cooked up out of many years of trying to understand how to renormalize in curved spacetimes. And it's a prescription that has been constructed in order to satisfy a set of axioms which are called Waltz Axioms, as in Walt, the guy that wrote the relativity book. Is that same guy? And also the guy that wrote the curved spacetime quantum field theory little red book. Is that same guy? Okay. So yeah, so let me tell you what the axioms are for renormalization. And then I'll give you the prescription that implements all those axioms, that satisfies them. Okay? So if you have a state omega 1, okay, and its 2-point function, its Weidmann 2-point function minus the Weidmann 2-point function of a state omega 2 is smooth, then it better be that the renormalized stress energy tensor here, well, let me write it like that, minus the renormalized stress energy tensor here is smooth. So I'm explicitly writing the points, but you understand that these are functions, right? So if the difference of the Weidmann functions in 2 states is smooth, the difference of the renormalized stress energy tensors better be smooth. That's the first axiom. The second axiom is that, well, the second axiom, let me write it like this, is a local covariance axiom. And this is a technical point that I will not explain, but it has to do with the following idea. If I take an expression for the renormalized stress energy tensor defined on some spacetime, and then I take this spacetime and I embed it isometrically in a larger spacetime, okay? And I carry around the expression for the expectation value of the renormalized stress energy tensor, such that the state is now defined in this region in the larger spacetime. Then this should remain invariant, okay? So that you shouldn't then get something that is non-renormalizable after you did the isometric embedding or something like that. That's the idea, the general idea. This goes by the name of local covariance. So local covariance of TAB Ren, okay? Now, for all states this condition should be satisfied. Okay, so conservation of the energy momentum tensor, covariant conservation. And finally, the last condition is that if you go to the Minkowski vacuum, then if you go to the Minkowski vacuum, then this should be 0. That's the last axiom. So it's 4 axioms. Okay? And the prescription that satisfies all these axioms is the following. Is the following. Is a limit when x prime goes to x of some operator TAB prime, so which depends on x and x prime, of the Weidmann 2-point function minus the Hadamard parametrics like that, plus another tensor which I'll tell you what it is now. So what is TAB prime? It's an operator that takes a covariant derivative in x and a covariant derivative in x prime. Plus, again the same story, this x on x, this x on x prime, plus m squared plus psi x. Okay. So this operator acts here and there, and in such a way that the distributional singularities are taken care of by this subtraction. Okay, and then you take the limit. Okay, PAB is a local symmetric tensor correction required for covariant conservation. That is axiom 3 of Waltz. So in other words, if you would just ignore this and think that the definition of the renormalized stress energy tensor is just that, which is well motivated from the classical form of the stress energy tensor, you would find that it's not covariantly conserved and that you need to add an extra term to guarantee covariant conservation. And this term is usually, well, it equals V1 GAB. And what is V1? Do you remember those coefficients that we obtained from the Hadamard recursion relations, the little v coefficients? V1 is the coefficient 1 of all those n coefficients. And this bracket means in the limit when x goes to x prime. Okay? And this gives you a trace anomaly. A trace anomaly when you have conformal field theories. Okay? If you have a conformally coupled Klein-Gordon field, this is responsible for the quantum trace anomaly, this term. It is also intimately connected to Hawking radiation. So Hawking radiation stems from the trace anomaly as well of the stress energy tensor. And next, you can add you can add of local geometric terms. You can add geometric terms to this as long as you don't break break the axiom. So in particular, you can add, for example, the following geometric terms, GAB, and then there's some other tensors cooked out of G and curvature tensors, which are typically referred to as HAB1 and HAB2, that are typically of the form Riemann contracted, Ricci contracted, Ricci squared, and so on. And all these terms you can add, and they are ambiguous, okay? And where does the ambiguity come from? Well, remember that when we define the Hadamard parametrics, okay, we had something like 1 over 2 pi squared sigma epsilon, and then here we had the V log sigma epsilon divided by lambda squared. And so the ambiguity comes from lambda squared being an ambiguous term. And so you can, this is a length scale, and you can put whatever length scale you want in this renormalization. So if you go from some lambda squared to some lambda prime squared, you will get that this expression spits out some smooth coefficient terms that in turn go and contribute to the smooth part of the. So remember that we had this. If you change the prescription, if you change the scale, you will change the contribution of the Hadamard by distribution by a smooth term, which you then reabsorb to this, and which then appears in this subtraction here, right? So each time you change the length scale, you're getting a different number, a different function of x here, and those functions differ by combinations of this sort, which are terms that are geometric and locally conserved in this sense. Okay, so this ambiguity gives rise to these terms. And let me just say that the ambiguities here will have to do with the renormalization of the cosmological constant, if you think of it coming from the action, right? So the terms in the action that go like this are the terms in the equations of motion that go like this are the terms that go in front of the cosmological constant. The terms that in the equations of motion of the semi-classical Einstein equations go like this are those that have to do with G Newton, right? If you remember the Einstein field equations. So G AB minus lambda G AB equals 8 pi G Newton TAB. Okay, so these terms have to do with the renormalization. So terms that contribute like this in the ambiguity have to do with the renormalization of G Newton. Terms that contribute like that have to do with cosmological constant. And there's two other constants which will also run, but that are entirely quantum, that have no counterpart in this situation, because what you will have here is that the renormalization of the stress energy tensor will give you terms, for example, that go like RABCD, RABCD, or like RAB, and so on. These kind of terms that do not appear in the Einstein-Hilbert Lagrangian. So what you have to do is you have to write a new Lagrangian, which is the Einstein-Hilbert Lagrangian, which is the Einstein-Hilbert Lagrangian with cosmological constant, plus some other Lagrangians, which are geometric and have the right weight. So,
are they going to act as a counter term or something like that?
They could, in principle, in principle, these are the kind of counter terms that you expect that will appear in quantum gravity. And they appear already at the level of semi-classical gravity in this sense, right? So you will have some L tilde, right? Some other terms that when you vary, you get some extra. In other words, you could imagine that this is the Lagrangian and you have the quantum Klein-Gordon Lagrangian. And then you do the renormalization of the stress energy tensor and you realize that you have these ambiguities that keep giving you these terms which are like Riemann squared, Ricci squared. And then you realize, oh well, so the full action might as well just be an action that when I take the variation gives me already terms of this sort in the, so let me do it like this, in the equations of motion, and then these coefficients will go into renormalizing those coefficients in the equations of motion of the whole semi-classical theory. And let me just emphasize, in case you're thinking that perhaps what would be convenient is to make those coefficients appear in such a way that you can write a Lagrangian that when you write the semi-classical Einstein equations, they cancel these terms, and all you're left with is the standard second order problem. But the thing is, you can't do that. Like, there's no way that you can eliminate those terms, because in particular they appear here, which is necessary for the conservation of the stress energy tensor, the renormalized stress energy tensor. So there's no way to cancel the terms that, go like this. They will generically appear, even if you ignore these ambiguities, they will generically appear here at the level of this extra contribution that you need to guarantee, in order to guarantee axiom 3 of Waltz axioms, and which in turn gives the trace anomaly for conformally coupled blah 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 theories, and is the origin also of Hawking radiation, for example. It's a very quantum feature, and so it's unavoidable. And this is a big problem for semi-classical gravity, because if you try to write the equations of motion as an initial value problem, you will realize that these terms spoil it. And this is no longer a second order well-posed problem for the Einstein equations with a scalar field. It becomes something that it has solutions that are so-called running solutions that you start with data and they bifurcate. It's not a second order problem, meaning in principle you should give more than initial values and initial momentum and so on. So it's a really big problem, and I think up to today nobody knows really how to do semi-classical gravity with full control, right? Okay, so people
try to relax axiom number 3.
Have people tried to relax axiom number 3?
I mean you and your group?
No, I've never tried to relax axiom number 3.
Because why should the expectation value of the energy momentum be conserved?
Yeah.
Right?
Well, of course, people like Daniel have reasons to believe that it will get violated in some ways and whatnot. And it is, in a sense, this is an expectation value, and you expect that measurements will violate condition 3 and so on. But what you mean by semi-classical gravity is to really try to use this, it's really replacing by the expectation value. You could try to go beyond that. So, for example, there's the work of Baylock-Hu and I forget who else. Somebody else. Somebody who starts with a V, maybe. Okay. Then two mainly. They work on something called stochastic gravity, which tries to add some stochastic terms and argues that this is, they argue that this has to do with fluctuations of the vacuum and so on, and they try to put them in the semi-classical Einstein equations and try to get somewhere from there. I'm not sure where they get to, and I'm not trying to undermine what they do. I think what they do is extremely interesting, but I don't understand it, so I cannot comment further.
Benito, why do you have only 4 ambiguities, so to speak?
Right. Yeah, I mean, these are the terms that crop up if you do the calculation, but you can collect them in such a way that that they come naturally from the most general Lagrangian that you can write, that has in which each term is a 4. This is in 4 dimensions, in which each term is a 4 form, right? So that you can integrate it into an action, right? And you can only write so many terms like that. So and you have to write them in such a way that that when you get to the equations of motion, they don't spoil this condition. So they will respect this condition, and in addition, they have to have the right weight in the Lagrangian. That's why you have only so many terms, and they have a very precise. Well, of course, and local Lorentz invariance and Diffie invariance. And if you're, well, Giaccanini and Folacci give very explicit expressions for those ambiguous terms. But also, if you go to Birrell and Davis, which is that monograph from the 80s, 82 or so. Birrell and Davis also explain what those ambiguous terms look like and what terms in the Lagrangian give you those kind of terms upon variation. But they're long expressions, and it's not worth to write. It is, I think, better to just discuss what the philosophy is. They're just complicated term in terms of the Weil tensor, the Riemann, and so on and so forth. Okay. Maybe we don't have a lot of time now. It's already 12, so we're missing 2, Hawking radiation and anti-de Sitter stuff. If you want, I can continue. We can go very quickly. Maybe in half an hour, I can give you a flavor of everything. I think there's no class, apparently. Let me see. I think there's no class. I can go for half an hour and tell you the main idea and the references, and you can then go and check if you're interested. Or if you really want me to give you details, I can do it next week. But I think for Yuri, this is not a good idea, and so on. Okay, so up to you, guys. Well, I'm also happy. I'm happy to talk to you about this in private as well. But what do you guys want?
I would prefer it next week.
Yeah, Cristobal, you as well?
At least that's safe.
Yeah, everyone. Okay, so we leave it for next week, and you and I chat over lunch. Okay, thank you. So that's it for today.